So Gauss law of magnetostatics or Maxwell's second equation. What is the Maxwell first equation? Maxwell first equation, del dot D is equal to rho or del dot E is equal to rho by epsilon naught. So this is the Maxwell first equation. Maxwell's first equation, you should remember Maxwell's first equation. So Maxwell's second equation we will go to derive. This is del dot B is equal to 0. This is the Maxwell's second equation. You remember. Del dot B is equal to 0. You can also write here. So how can we define? This is definition. Del dot B is equal to 0. Del dot B is equal to 0. This is explanation. Del dot B is equal to 0. The divergence of magnetic field induction is equal to 0. Or del dot B is equal to 0. The divergence of magnetic field induction in a closed surface is equal to 0. That is called Gauss law of magnetostatics or Maxwell's second equation. Maxwell's second equation. So the magnetic flux, you know very well this formula, equation 1, you know very well. The magnetic flux through an element of area ds is given by the dot product of B which ds. So mathematically we can write phi is equal to surface integral of B dot ds. This equation is known as integral form of Gauss law. Integral form of Gauss law. So we will give another one. Already we discussed in our introduction, phi is equal to surface integral of B dot ds in our previous class. You can see in our previous class, I am showing here. So this is already magnetic flux density. Same principle. I am going to use phi is equal to surface integral of B dot ds. You see here. So this is the basics, magnetic flux density or magnetic field induction. Already I discussed phi is equal to surface integral of B dot ds. So same value I am taking here. You see here. So the magnetic flux through a closed surface is given by phi is equal to surface integral of B dot ds. So it has integral. This is integral form of Gauss law. What is B? B is the magnetic field induction. Magnetic field induction. You see here, for example, this is some area of the material. The magnetic lines of force entering and coming out same number. So entering and coming out, entering and coming out, same number. You see here, the number of lines emerging from any volume bounded by a closed surface is, closed surface S is always equal to the number of lines entering to the volume. What I am saying, the total number of lines, the total number of magnetic lines of force are entering through the material is equal to emerging from the material. Same. So this is phi 1 is equal to phi. This is phi 2 is equal to phi. What is phi? Magnetic flux. What is magnetic flux? The total number of magnetic lines of force are passing through the certain area of the material is called magnetic flux. What I am saying? So what is magnetic flux? The total number of magnetic lines of force are passing through the certain area of the material is called magnetic flux. The entering magnetic flux is equal to emerging magnetic flux. Both are same. Phi 1 is equal to phi. At this is phi. This is also phi. So the resultant phi minus phi, what is that value? 0. You should remember. Phi is equal to 0. What I am saying, the number of lines emerging from any volume bounded by a closed surface S is always equal to the number of lines entering the volume. The entering magnetic lines of force is equal to emerging magnetic lines of force. So the magnetic flux entering into the material is equal to emerging magnetic flux. So resultant magnetic flux through what I am saying, hence the flux of B through any closed surface is equal to 0. Thus, the magnetic flux phi is equal to 0. The phi is equal to 0, just to substitute in equation 1. So what is equation 1? Phi is equal to surface integral of B dot ds. Just to substitute, this is 0. This is 0. So surface integral of B dot ds is equal to 0. This is equation number 1. Surface integral of B dot is equal to 0 because magnetic flux 0. So dividing with this value, this equation, dividing both sides of the equation 2 by an incremental volume delta V. So I am taking same surface integral of S B dot ds is equal to 0. Dividing with delta V, both sides. So you can observe here, same. So what about this? This is 0. 0 by something, 0. This is, we can write delta V, surface integral of B dot ds is equal to 0. You can see in next slide. So here, same, up to here, same. So this is 1 by delta V. What I am saying here, 1 by delta V, remaining surface integral of, this is as it is, I am writing here, B dot ds is equal to 0. This is equation number 3. Both are same. When volume delta V, the small volume delta V tends to 0, 1 by delta V surface integral of B dot ds is called del dot B, divergence of B. Already I discussed it in Maxwell first equation. Same formula. At that position, 1 by V surface integral of E dot ds. In first, 1 by V surface integral of E dot ds. This is equal to del dot E. I discussed in our previous class. So similarly, this is 1 by delta V surface integral of B dot ds. This is called the divergence of field B. Divergence of the magnetic field B is represented by del dot B. Again, remember, in this formula, the small volume delta V tends to 0. 1 by delta V surface integral of B dot ds is called divergence of magnetic field induction B. The divergence of magnetic field induction is represented by delta B. So this is equal to delta B. Del dot B. So 1 by V, what is this? Delta V, surface integral of B dot ds is equal to del dot B. Divergence of, this is called divergence of B. That is called divergence of field. Divergence of the magnetic field B is represented by del dot B. So same right side, this formula is equal to del dot B. Substituting, you observe here, left side in equation 3, left side in equation 4, both are same. So we can write equation 4 in equation 3, del dot B is equal to 0. This equation is known as point form of Gauss law of magnetostatics, or differential form of Gauss law, or Maxwell's second equation, or Maxwell's second law for magnetism. Del dot B. First equation, del dot D is equal to rho. Second equation, del dot B is equal to 0. Maxwell first equation and second equation. This Maxwell 1 and 2 equations are called static Maxwell equations. Static, electrostatic. This is electrostatic first equation. This is magnetostatic second equation. These are called static Maxwell equations. Again, you see, I am giving here, again discussing. So Gauss law of magnetostatics or Maxwell's second equation, del dot B is equal to 0. So the divergence of magnetic field induction in a closed surface is equal to 0 is called Gauss law of magnetostatics or Maxwell's second equation. Explanation. The magnetic flux through an elemental surface area phi is equal to surface integral of B dot ds. This is equation number 1, where B is the magnetic field induction or magnetic flux density. So up to here, you just remember phi is equal to 0. Just, it represents just phi is equal to 0. Because in a closed surface S, for example, this is the closed surface, the entering magnetic flux is equal to emerging magnetic flux, both are same. So resultant phi minus phi is equal to 0. You can see here, the number of lines emerging from any volume bounded by a closed surface S is always equal to the number of lines entering the volume. The entering total magnetic lines of force is equal to emerging lines. So magnetic flux 0. Magnetic flux 0. This magnetic flux 0, substituting in equation 1. So same phi is equal to 0, just substitute in equation 1. Then we get surface integral of B dot ds is equal to 0, equation number 2. So dividing with delta V both sides, you can see here, dividing with delta V both sides. So we can write this is 1 by delta V, remaining surface integral of B dot ds is equal to 0 by something, this is 0. When this delta V volume tends to 0, this term represents that del dot B. This term represents that del dot B. Clearly, I mentioned here. When volume delta V tends to 0, this 1 by delta V surface integral of B dot ds is called the divergence of magnetic field. It is represented by del dot B. So this value is equal to del dot B. I am writing here del dot B. In equation 3 and 4, comparing del dot B is equal to 0. This equation is known as point of Gauss law of magnetostatics or differential form of Gauss law or Maxwell's second equation. Maxwell's second equation.